Hey everyone, this is the Chapter 7 review video. We're going to go over work, different types of energies, how to use the conservation of energy equation, and power. First, let's talk about work done by a constant force. Work is done when a force causes an object to move. So let's say we have an object and there's a force applied to it. Let's say the motion is to the right in the x direction. To find the work, we need to find a component of the force that is parallel to the motion. In this case, it would be Fx. Once you find Fx, you multiply it by the distance traveled, and that will give you the work done. The SI unit for work is the joule, which uses letter J. So, for example, you push on a stationary brick wall with a force of 200 newtons for 30 seconds. How much work do you do on the wall? So remember, to find work, you have to multiply a force by a distance. In this case, the wall is stationary. That means that the wall does not move. That means there is no work. So if there's no motion, there's no work. It doesn't matter for how long you apply the force. We also need to know if the work done on an object is positive, negative, or zero. When we have positive work, it means that the force is in the same direction as the displacement. We have negative work when the force and the displacement are in opposite directions. And we have zero work when the force is perpendicular to the displacement. So whenever you calculate work, always ask yourself, what is the sign of the work? Let's look at an example. Find the work done by gravity on a 10 kilogram mass as it is pushed 5 meters up the incline. So we look at this object here, it's pushed up. Let's look at the forces acting on it. There's an applied force to the right. Because it's on an incline, there's a normal force perpendicular to the incline, and the object has a weight going straight down. A lot of times you're going to be asked for the work done by a specific force. In this case, the work done by gravity. So remember the equation that we just talked about. The work is equal to the component of the force parallel to the motion times that distance traveled. So the motion is up the incline. Delta x is up the incline. So we need a force parallel to the incline direction. If we look at the weight, we know it has a y component perpendicular to the incline, and it has an x component parallel to the incline. If you remember back from chapter 4, when we have an incline, we rotate the coordinate system so that the x-axis is parallel to the incline, the y-axis is perpendicular to the incline. So to find the work done by gravity, we need Fgx, the x component of the weight multiplied by the displacement. The x component of the weight is opposite to the angle of 30 degrees here. So this component, Fgx, is going to be mg sine theta. And then we're going to multiply by delta x. But let's not forget the sign of the work. The force is going to the left while the motion is going to the right. Because they're opposite each other, that means that the work is negative. So let's not forget to write a negative in front of the work. When we plug in all of the values, negative 10 for the mass, 9.8 for g, sine of 30, times 5 meters for the displacement, we're going to get negative 245 joules as the work done by gravity on the block as it moves up the incline. Now let's look at energy. We've talked about different types of energies in this chapter. First, kinetic energy. We have kinetic energy due to motion. In this picture, we see a ball with a speed v and it's moving to the right. Because it has speed, it has kinetic energy, which is given by Ke equals 1/2 mv squared, where v is the speed of the object. Then we have potential energy. An object has potential energy due to height. In this picture, we see a box, a ball, which is a height h above some surface. So we typically need to label the surface or the ground level as y equals 0 so that the height of the object can be measured relative to that reference level. Because it has a height, the potential energy, PEG for gravitational potential energy, is equal to the mass times g times y, which is the height above that reference level. And then we have spring energy, which is due to a spring. Whenever a spring is stretched or compressed, it's going to have spring energy. In this picture, we can see that this line right here is the relaxed position of the spring. So the top spring here is stretched by an amount x. Because it is stretched, that means it has the spring potential energy, PES, equal to 1/2 kx squared, where x is the stretch or the compression, and x is the spring constant, which measures the stiffness of the spring, and it's usually given. The SI unit for energy, no matter what type, is going to be the joule, the same unit as work. Let's look at the work energy theorem, which relates work and kinetic energy and tells us that work changes the kinetic energy. It's written as the net work equals change in kinetic energy. As we can see in this picture, when a car skids, there's some force acting on it, such as friction, to stop it, and it's going to travel a certain distance before it stops. So because of the work done by friction, the speed or the energy of that object is going to change. Let's look at an example. What happens to the stopping distance if the initial speed is doubled? So this is referring to a car skidding. Now we can see from this picture that as the speed is doubled from 45 to 90 kilometers per hour, that the skidding distance increased by a factor of 4. But we can figure that out using the work kinetic energy theorem. We can write it this way, where the net work is just the work done by the force of friction, which I'm just calling F here. So F times delta X equals 1/2 mv final squared, which is the final kinetic energy, minus 1/2 mv initial squared, the initial kinetic energy. This right-hand side is a change in kinetic energy. So if we're looking for stopping distance, we can solve for delta X. We know that when we're skidding, that the final speed is going to be 0. So that means the final kinetic energy is 0. So when we solve for delta X, we're going to have negative 1/2 mv initial squared over the F. And we want to see how does doubling the speed, how does it affect the stopping distance? So we're going to rewrite the equation, and this time we're going to double the speed. We're going to leave everything else the same. When we double the speed, remember that the whole 2v initial is squared. Nothing else has changed, but once that factor of 2 gets squared, we can see that we're going to get 4v squared instead of 2v squared here. And then we can bring that factor of 4 to the front, and we'll see that we have 4 times negative 1/2 mv squared over F. I like to leave the 4 separate from the factor of 1/2 so that we can compare the new stopping distance to the old one, and we can see that it's 4 times as much, just as we expected. Next is the law of conservation of mechanical energy. It states that energy cannot be created or destroyed, but it's just going to be transformed from one form to the other. We can write it as the sum of the initial mechanical energy, which is the sum of kinetic and potential energy, equals the sum of the final mechanical energy. We can write out this equation, expand each term. It looks a little bit intimidating, but let's see what each term refers to. They're all the terms that we talked about a couple slides ago. So whenever you have speed in a problem, that means you're going to have kinetic energy. Whenever you have height in a problem, you're going to have potential energy, the gravitational type. And if there's a spring in a problem, you're going to have the spring potential energy. So what you're going to want to do when you solve problems, you're going to want to think about, in the initial and final case, is there a speed, is there height, is there a spring, in order to figure out what terms you're going to keep in the equation. In the picture on the right, we can see that a person is falling down. The sum of the potential and kinetic energy remains fixed as at 10,000 joules, but we can see that as the person goes down, the potential energy goes down while the kinetic energy goes up. And this is very typical when we have conservation of energy problems, we see that there's a change in height and a change in speed, which leads to a change in potential energy and a change in kinetic energy. So whenever you can imagine a person either falling or an object going up, you have that change in speed and change in height. That's a good indication that we're going to use conservation of energy. So let's look at an example of how to use this equation. Here we have a 5 kilogram box that slides up a frictionless 30-degree incline at 10 meters per second. What is its speed after traveling 4 meters along the incline? So we see this problem and we see that there's a change in height as it's going 4 meters up the incline here. And the speed is changing as well. So let's use conservation of energy. The first thing we're going to do is label the diagram. When we're dealing with potential energy, we want to label that height y equals 0, which is going to be the lowest height in the problem that we care about, in this case, the lowest position of the box. That's going to be the initial height. And then the final height is going to be how high it gets. So we're going to label that as YF. I also like to show that it is moving initially. There is some V initial initially. And then at the end, there is some V final. Sometimes it stops at the end, but in this case, there's no indication that it's stopping. It doesn't say it's a maximum height, which would indicate stopping. So we do have a speed, and that's what we're actually looking for. The next thing you want to do is cross out the terms equal to 0. So you're going to write out the whole conservation of energy. Cross out what's equal to 0. First of all, there's no spring in this problem, so there's no spring energy. That makes our equation a lot more simple. Now let's go through each term one by one. We do have speed initially, so we do keep the kinetic energy term. Now initially we don't have any height because we call that our 0 level for height. So we can cross out the gravitational potential energy initial. And then for the final energies, we do have kinetic energy because we have speed, and we do have gravitational potential energy because we have height. So this is the equation that we're left with. Now we can solve for the unknown. First, let's go ahead and cross out the mass because it's present in all of the remaining terms. And let's write down what's left. 1/2 V initial squared equals 1/2 V final squared plus GY final. Our equation is now a lot more simple, and we can solve for V final. Since I don't like fractions, I'm going to go ahead and multiply everything by 2 to get VO squared equals VF squared plus 2GY final. And now I'm going to subtract 2GYF from both sides to get VF squared by itself. And now I can take the square root of each side to get VF by itself. It's going to equal the square root of V initial squared minus 2GY final. Now, the one thing that we forgot to do is to solve for that final height. The final height is not 4. Height is measured relative to the initial height. Height is a vertical distance, so we need this vertical distance here. We can see that there is a triangle formed with the hypotenuse being 4 meters, and the angle here touching the horizontal is 30 degrees. So we can see that that vertical side is opposite the angle, so it's going to use sine. This y final here is going to equal 4 sine of 30 degrees. And that's going to equal 2 meters. So usually it's good to calculate this height when we are labeling the diagram. Now we're ready to plug in our values. The square root of 10 squared, that was our initial speed, minus 2, 9.8 for G, and 2 for the final height. Plug all of this in, it's going to give us 7.8 meters per second. So this is how you solve the conservation of energy problems. When you see that change in height and that change in speed, go ahead and set up your equation. Now, what about when we have friction? Friction typically does negative work, at least in all of the problems that we're dealing with. So we can take our conservation of energy equation and add this term, which is the work done by non-conservative forces, and friction is one of those non-conservative forces. So is air resistance, which we also see sometimes. But if you have a problem with friction, what you're going to do is you're going to replace that work done by non-conservative term by minus FKD. And that's because the work done by friction is going to be negative, and it equals the kinetic friction force times the distance traveled. So let's take a look at an example. A child gets a slide burn while going down a slide. What happens to her mechanical energy? We said earlier that mechanical energy is the sum of kinetic and potential energy. So that means that the initial mechanical energy has all three terms here on the left. The final mechanical energy has all three terms here on the right. So what happens to this energy? It does not remain constant because the work done by friction causes some of this mechanical energy to be lost. It's not lost forever, it's just transformed to a different form, such as heat. So that means that our initial mechanical energy, which I'll call MEI, is actually greater than our final mechanical energy, which I'll call MEF. And that's because we've lost some energy to our surroundings here due to the non-conservative force of friction. Finally, let's look at power. It's the rate at which work is done. So how fast you're doing work per time. We can use force times distance for work to get force times distance divided by time for power. The SI unit for power is the watt. We use the letter W for this unit. Let's look at an example. A forklift's power doubles. How much more load can it lift in the same time? Well, power is going to be our force times our distance divided by time. And the load, the force that we're going to use to lift the load is just going to be the weight of the load. So we can see that if we have twice the weight, 2 mg, and the distance and the time do not change, then that's going to give us twice the power that we had before. So if we have twice the power, we're going to lift twice as much load. So that's it for the Chapter 7 review video.